thank the organizers and the administration of EHES for possibility of presenting some results which were obtained in the collaboration with Gérard Duchamp, Maxime Kontsevich, and Gleb Koshevoy. And here's the plan of my talk. The title is Algebraicity Beyond Beukers-Heckman and Bober, Emerging Patterns. So first I will talk about integer sequences and their generating functions. Then I will mention briefly criteria for algebraicity for single hypergeometric functions which are generating functions of these sequences. And then I will mention the families of Bober, which are exemplification of the criteria of Beukers-Heckman. And then I will talk about some open problems and about parametrization of the problem. And then essential thing which appears to be new, these are extensions of the situations which do not comply with the criteria of Beukers-Heckman and Bober. And I will give a couple of examples which will explicitly show that the word defined by these authors in the title is limited and that there are things which are beyond it. So there is no theory behind my presentation, but there will be a census of some small number of examples, and I will appeal to experts to draw some more conclusions. So let me say, we have here a very simple presentation of criteria of Beukers-Heckman, which dated from '89. I'm sorry for these green scriptures, which are not very well visible. So we have a, oh sorry, there is no, no.
On the left.
No, no. Okay. Okay, so we have, but where is the pointer?
Yes, near the end. You must, yeah.
Yes.
Oh, this is green. Why is this green?
Because it's green.
Okay. But now?
It's logical reason. It's fashionable.
Yeah, but now there's no pointer.
See,
do you have a pointwise pointer?
So you have to press.
Yes,
in order.
press a point.
you should be careful. Just yes.
Oh, okay. So it's not, the pointer has a problem of Heisenberg relation. So rho of n are integers which enter into the play, and now this is the ordinary generating function, and once we choose rows of certain in certain way, then the generating function is a generalized hypergeometric function of certain order, of certain parameter p minus 1. Upper parameters are p of them, lower p minus 1 of them, and there's a coefficient of z here in the argument, which is a, and a is related to rho in the following way. A is n goes to infinity, rho of n over n. Okay, so you have the set of parameters, and you have this generating function with this argument. And now the criteria of Beukers-Heckman for this particular case, where there is only one hypergeometric function, are the following. This generating function is algebraic if the set of upper parameters interlace, set of lower parameters interlace the set of upper parameters. Okay? There are some assumptions, but the main idea is interlacing of parameters. And
you should multiply these things by any number compared to denominators.
Yeah, I said this is a simplified version.
It's not not sufficient criterion.
Okay, but for my purposes, for my examples, I use this simplified.
Because it's been the ratios of factorials. Yes.
Yeah.
But they are integers. U's and L's are integers, or not?
No.
No.
U and L's are rational numbers.
Rational numbers. Yeah. Okay.
And here you get fractional parts of U, not.
Yeah. Okay.
Are integers.
So,
yeah.
For my examples, this formulation is enough. Okay. So many and before I go to my set of examples, I will show you that there are some combinatorial numbers for which situation is a little bit more complicated. Namely, if we take shifted binomials of this form, p is larger than 0. Usually in our application, it can be a rational number, and r is real. Then if I construct the generating function parameterized by pr and the parameter z, which is defined here, for low values of p, which are integers, like 2 and 3, for 2 we get something which is purely algebraic. By the way, these two components are related to known generating functions. These are Catalans, and these are central binomials. For 3, we get a single hypergeometric function of type 3, 2 for all r's. Okay? So this is for p, which are integers. But there is an important observation that when p becomes rational, like 3/2, for all r, this generating function becomes the sum of 2 hypergeometric functions. And for arbitrary r, which are real, we can give a formula for that. And, well, the formula is like any other formula. But there are one thing which I point out. In the formulas of Beukers-Heckman, we have argument which is z. Here you have argument which is z squared, which you can understand from the derivation. But the important point is that for p equal, when you have 3/2, then you have 2 generating functions, 2 hypergeometric functions, which are generating functions. So if there will be algebraicity, this will be not in the framework of Beukers-Heckman already. So for 3, for instance, for 4 thirds, there will be 3 hypergeometric functions, and so on and so on. So then our modest objective is to see the examples, explicit examples, how can we obtain algebraicity in this kind of framework.
To summon algebraic, this one.
Yeah.
That further.
Yeah, okay. So first I will now refer to the classification of Bober, which dates from 2009. He has classified and given examples of sequences of moments which do satisfy the criteria of Beukers and Heckman. And it's a very interesting scheme because it comprises 3 series of simple expressions which are parametrized by integer a and b. For the second series, a must be larger than b, and there's a third series. And for all a and b integer, these things are moments which are leading to single hypergeometric function which will be algebraic, okay? But there are some open questions. There is a family of 52 another unparametrized examples of moments which are listed in his paper, and I will now give you the very practical reference to these 52 sporadic cases, because in the famous online encyclopedia of integer sequences, which was conceived and taken care of Sloan during the last 60 or 70 years, 60, let's say, which has the following address: https org. Okay, I am referring to the point 4. You enter that, and you will get a complete list of entries in the encyclopedia which are referring to these sporadic cases, which have formulas but no parameters. What you have to enter is the following thing. This is a fellow who took care of all that. He has 52 entries, and he collected all information about these sporadic cases with references and so on. So it's very practical.
Excuse me, I just didn't understand. UNs are just, you take any set of this set as a parameter. You have finitely many parameters, and here we have infinitely many.
Here I have 2 parameters, A and B.
3 infinite families.
3 two-parameter families.
Yeah.
Infinite, yeah. And
Infinite.
Exotic example.
But your hypergeometric function depends on finitely many parameters.
Yes, yeah. No, but larger, yeah.
So for any integer a and b, any member of these 3 series will give you a hypergeometric function, single one, which will be algebraic. But on the top of these 3 series, there is a 4th family, which is worked out here in detail, and there's a proof that they are also giving algebraic hypergeometric functions, although they are not parametrized. Okay, so now this is the situation of Bober, and I can give you maybe one example out of all of them. And this is, so I mentioned that here entries are 6 digits numbers. So these are just, this is a numbering of sequences in this database. And for instance, A this one is equal to okay. So this is one of the examples of such sequences. And you can say, okay, we know that generating function is algebraic, but what would be the order of the algebraic equation? And there are no statements, as far as I know, about the order of algebraic equation. For all of them?
For all of them, yeah. Yeah, sure.
They are not published.
Yeah, but it's Beukers-Heckman, it's a whole Mellin group. It's
It's the order of the groups.
Yeah, something, maybe some stabilizer or whatever. Yeah. Essentially, it's order of course.
But I know only of one.
But they did not write it in the inventionist.
No.
Okay.
No, but it's very easy, yeah, if you look information.
What?
No, it's very easy to find.
Okay, maybe, yeah. At least I don't know.
Yeah. I can reconstruct.
Okay, great.
Okay.
But if I understood correctly, that UN in this slide is what was row n in the previous
Yes.
one. Okay.
Yeah.
And you and the previous slide is it's nothing to do with the okay.
Yeah.
That's fine.
Rodriguez Villegas gives some orders. Yeah. Okay. But am I right that it was not published?
But it's very easy, yeah.
But you get the bound, not the irreducible.
No. I think it's the whole story.
Irreducible.
It's
Huh?
yeah, the whole the degree of algebraic equations. It's easy to deduce from this Hausdorff groups. Yeah, sure.
I will.
Yeah.
Okay. So it's very interesting. Okay. So now for one situation concerning this Bober classification, one can, at least to my now knowledge, derive a parametric expression for the algebraic equation. And I will explain what I mean by that. You have Pn over n, P equals 2, 3, which is evidently giving rise to algebraic equation. But what will be the form of the algebraic equation as a function of P? Okay, so if I write generating function, so Pn n, Zn, there will be a parametrized form for the algebraic equation, which is the following. If I call it G, then this will be P to P Z G P plus P minus 1 G plus 1 P minus P. Here's P minus 1 G plus 1 P minus 1 equals 0. P minus 1 G equals 0. So this is a parametric equation. So this set of moments, which I call rho n, it's a member of family Roman 1. Okay, so for that you can write, not only you can say that this is algebraic, but you can write down explicitly this algebraic equation. Okay. Now, we have attempted to characterize more all these sequences, seeking the integral representation of them in the following term: rho of n equals integral of 0 x n times w dx. Okay, and here is quantity which I called S, which is support of this w of x, which we call measure. Okay, sometimes for certain rho n's, it can happen to be positive. Then rho n's are moments of probability.
Is it dx or dx over x?
This is x.
Yes, but the differential, is it dx or dx over x?
No, dx.
Ah, okay.
Yes, okay, dx.
Hausdorff then.
Yeah, yes.
Okay.
We solved the problem of Hausdorff moments in order to find the function which is characterizing this sequence. And in most of the cases, it is possible. And the series of most of the series of Bober, which are classified here, give rise to explicit functions which we can write down. And as far as I know, most of them are positive. So the moments classified here give rise to probability measures. Okay? We are using for that the method of the inverse Mellin transform, which is equivalent to the application of the so-called Meyer G functions, which are defined here. I will have no time to go over that. But Meyer G functions are inverse Mellin transforms of the ratios of gamma functions. And since we have in these classifications of Bober the whole zoo of fractorials, of course we are dealing with gamma functions, and they are ideally suited for the treatment using the Meyer G functions. Okay. But now I am going to present you several examples of the things which do not fit to the classification of Bober. Okay, I'm sorry because I copied from the screen and it's not very well visible. So let me just check to write at least the moments. Okay, so the moment which is in the top of the slide is 14 times 3n binomial 4n over 3 plus 2, 3 n, and everything is divided by n over 3 plus 1. So this looks rather unpleasant, but this is nothing special because binomial, these are gamma functions. So now the moments are expressible not exclusively by factorial, but also by gamma function. Okay? And now, if you calculate the generating function of this sequence, you will find out that this is not a single hypergeometric function, but they are three hypergeometric functions. I will not write down the whole expression which is here. You see this is here. Okay, so you see there are two hypergeometric functions for f3 and one 3f2. Okay, it's listed here. Now, first of all, we calculate the algebraic equation satisfied by these three hypergeometric functions. And it turns out to be of fourth order, okay? No, sorry. You see, fourth order. So the generating function, which is composed itself by three hypergeometric functions, is algebraic, and it has a fourth order algebraic equation. And now I am looking at the coefficients, upper and lower lists of coefficients. And as we see, we have three of them. And I looked at the common denominator, which is for the first one is 12, for the second one is 12, and for the third one is also 12. And what I see, that none of these three hypergeometric functions has interlacing lists of parameters.
No, it should go to fractional parts. Fractional parts are interlacing.
It's possible, yes.
Yeah, that's criterion. It's about fractional parts.
Yeah.
And you put them on the
One
circle.
circle, yeah.
Okay.
And with 0 for denominator.
Okay, so it means that every one of them is algebraic, and the sum will be also algebraic. Okay, but anyhow, it's not easily seen in this form. Okay? But, okay.
Please, Karol, is it always obvious that the sum of hypergeometric will be rational? Will be
So,
algebraic always?
That's what I think.
Sum of algebraic function, of course, it's
Yes.
algebraic,
Yeah.
Okay.
Yeah, okay. So now I am going to the integral representation of the above sequence. Okay, so I am looking at the function w of which characterize whose nth moment will be this sequence. Okay, so in the language of Meyer G function, it is a single expression, and in fact it is a sum of three hypergeometric functions. So these moments have this kind of weight function, which is characterized, and I can calculate the algebraic function, which is satisfied by the weight function, and what I find is essentially cubic algebraic equation, but in terms of the 6th power of W. Okay, so here we have this W, which is here. Okay, and now it turns out that it's where you take the 6th power multiplied by some numbers, it satisfies the cubic equation. So it is again algebraic. This is one example. And well, I here have given an example of this weight function, because this is somewhat different from the cases of Bober, because this weight function, as you see, is not a positive function, and also it is a rare example of function, weight function which has no singularity. In a sense, it's nowhere infinity. It has a negative intercept here, but so this is not a positive probability distribution. It is just a distribution, and of course the initial terms and other terms can be checked by integration. They just correspond to the terms in the sequence. So here we have this thing which is expected for algebraic equations of generating function, because they mirror also algebraicity of the weight function. So even in this case where only, let's say, gamma functions in these expressions appear, you can have an algebraicity of both components, algebraic generating function and algebraic weight. Okay. There will be a next small set of examples. How much time I got? 15 minutes, okay. So this is another example of rows which are again expressible through binomials. And you see here parameter P, and the expression is here. So you see here P plus 1 divided by P.
So binomial, it's kind of, you should put vertically.
Yes, yes, I should put it vertically, but I'm so involved with Maple that where you write it. So you're absolutely right, vertically. I'm sorry. Okay, so this is the sequence. Sorry. This sequence is listed here, and strangely enough, it is not in the Encyclopedia of Sloan, so it's a new sequence. And for p equals 3, it has a generating function which has here the sum of 3 hypergeometric functions. And again, the situation with the first one is interlacing, but the 2
The fractional parts are still interlacing. So
Yeah, okay, okay. So this is the fractional.
yeah. And Karol, you should be careful with encyclopedias. Have only 1 million entries possible, yeah, because of the 86 digits, yeah. Spoiled by.
That's it.
I understand. Okay. So now it can be. So the second objective is to write down a parametric equation for this generating function, which was considered here for general P. Okay, for general P, and in fact it is possible. So here I have written this equation, which is parametrized by P. Okay, so this one is somehow analogous to this one, which is also parametrized by P. And I give you an example here for P equals 4. And it is equation of order P plus 1. So it is 5. And it has these terms, okay? So there's one observation which I would like to make, is that the moments in the families of Bober are expressible through exclusively through factorials, not the gamma functions. So they are in a certain sense simpler than this kind of moments where you have a mixture of factorials and gamma functions. And there is a possibility of parametrized form of algebraic equation, whether to my understanding, in the case of Bober, such a possibility is not so easily done. First of all, the equations are of huge order.
I think for first family already it's kind of very.
For first family, you have here an example.
When you have parameters 1 and p minus 1, but when you have two general parameters, it's a mess, yeah.
Yeah, for general, it's a mess. Yeah. Okay, where in case here, it is relatively tractable, okay? So if I have another example, again, I'm sorry, I didn't write n. Well, this is also binomial. Yes, this is now right vertical. Yeah. Sorry, Maxime. Yeah. So this is another set of moments. Okay. So I give another set of parametrized equation, which is here. Okay. So this is of order p plus 1. And there is a second, I don't know why. Yeah, okay. Second, which is also correctly written, and it has this parametric equation for generating function. Okay? So these are examples. So you see that in case of these binomial expressions for moments, it is somehow possible to do to obtain a parametrized equation, whereas for Bober it's much more involved. Okay.
Yeah, but this kind of Lambert, yeah.
Yes.
The
first one.
Yeah.
As the second one's not.
It is.
Both, I think.
Both are related to Lambert equation. Yes. Okay. So now I am going to a last series of examples, which probably will comply with the Maxime remark. These are certain generalizations of Catalan numbers. So what are those? So you see, they are now parameterized by the number k, okay? And k goes from 0, 1, and so on. And n, of course, is a number, it's numbering moment, so it's from 0 and so on. So for k equals 0, it's Catalan. And the generating function for general k is here. And for Catalan, for k equals 0, it's trivial. Whereas for 1, for k equals 1 here, it is already one single hypergeometric function 3/2. And as I wrote here, it's non-interlacing, but fractional parts will be probably interlacing, okay? But what is funny about this example is that this function is an elementary function which can be expressed through radicals, okay? Now, for k equals 2, you have another single generating function in form of single hypergeometric function. Again, there is only very partial interlacing, and probably this will be the same effect as discussed by Maxime a minute ago. But what is observed that if you increase k, this partial interlacing will never complete. It will never complete.
That's a wrong notion.
Yes.
They should make go
Yeah.
fractional parts.
Yeah.
Yes,
Yeah.
but,
Okay. Okay. So
Yeah, yeah.
so now of course for this previous example there is also a possibility to obtain a parametric a parametric algebraic expression for all generating functions, which if I call generating function G, which depends on k, you have a parametric set of equations for generating functions, which are of order k plus 2. So, modulo remark of Maxime, these are examples of new kind of moments which have generating functions which fall into category of Beukers and Heckman, but have the distinct advantage of having parametrized form of generating functions, of algebraic equations for generating function. Okay, which is not the case for the previous series. That's all what I wanted to say.
Or maybe I just want to make a little comment. The last equations are this Lambert series. It's very, very simple. Yeah. Just to resolve the whole mystery. Yeah, this one equation, G series set for 1, and right plus Z to G for alpha and raised to power beta. And beta rational numbers. Yeah. It has unique solution in series, you just iterate it, and it has, for any two rational numbers, you get algebraic function. And you can rescale variable z to get integrality. And this is Lambert family, you have very simple formula for coefficients and binomial coefficients divided by n.
Yeah. I have this form here.
Yeah, function. Yeah, so that's 50% of equations.
Okay.
Yeah.
It's actually
The family, yes.
Yeah.
Just a small remark. Calling integral interlacing, because Beukers is around a circle, it's modulo Z.
Yeah.
But calling integral interlacing what you study the separation of partial interlacing could be of combinatorial interest. So you can this study.
You mean that the expression for moments are
Yes.
some have some combinatorial interpretation?
We can discuss. Yes.
Yeah, yes, probably. But I have consulted the encyclopedia, and there are some comments for certain cases, but generality is probably absent for generality. Okay.
I have another small question. Yes, in your zoology, do you have examples of sums of hypergeometric functions such that the sum is algebraic without two of them being non-algebraic?
Well, I have to check all of
No,
them.
no, I think it's almost not possible.
Impossible, because if you reduce this to a form,
Yeah.
you should have some normal form, because two of them could compensate, no?
No, I think it's very. I think the algebraic summations as well. Yeah,
For the terms?
yeah, I think so. Yeah. Okay. Otherwise, it's don't cancel.
Questions?
Okay.